Thank you, everyone. So I've actually been living in Australia now for quite some time, well over 20 years. And of the different Australian prime ministers, one of my favourite prime ministers is Paul Keating, who's famous for many things. But one of the things he was most famous for is describing Australia as the arse end of the world. Which is why it gives me absolute great pleasure, and it's a genuine pleasure, to be standing here in Gadigal country in such a beautiful location, being able to address you at the arse end of the conference. So this is about noise, and it's all part of a program, and like all of us here, we have various, we have sort of collaborators. I've just realized that that picture of me there, I had the beard, it was one taken after the beard. It was taken during COVID lockdown, and I appear to be wearing my bee suit. We're going to be talking about honeycomb codes later, so I just think it's vaguely appropriate. So this is about noise. So why do we actually care about noise, especially in the context of error correction? I mean, everybody knows everything there is to know about noise. Well, I mean, obviously, there are several reasons why we do. I mean, the first is that, if we know what's going on in the device, the people who are actually creating the device might be able to do something about the noise. They might be able to minimize it. I mean, perhaps, if we were interested in NISC, and I'm going to talk a little bit about that now, well, then perhaps if we know what the noise is, we can mitigate it. But the real reason, which we'll come to, is if we know about the noise, perhaps we can actually, this initial bit where we're trying to get a fault-tolerant quantum computer, perhaps that can actually help us just get over that edge and get something where our logical qubits are better than our physical qubits. So the thing with NISC, and there's a lot of excitement, or there has been a lot of excitement about using noisy quantum computers. I'm old enough to sort of remember the excitement when we had analog computers. Now, the reason why analog computers, of course, never succeeded was because they couldn't be error corrected. And the one advantage we have with quantum computers is the fact that they can be error corrected. So, maybe this was just a little bit about before my time. But sort of Andrew Doherty pointed out this superb analog computer, which was a Moniac. And this was a water-based analog computer that was used to model financial streams. And reserve banks actually used this computer to try and predict cash flow. Now, I have no idea whether this will actually play, but if it does, it's certainly worth just spending a few minutes watching.
So we'll do a couple of experiments today to show some of the basic sort of Keynesian macroeconomic mathematics. There are lots of metaphors about water and economics. There's sort of liquidity, there's income streams, there's cash flows. Well, this isn't a metaphor, this is an analog. It's a quantitative analog. And if I've got it all working right, I should get within about 4% of the correct equations. Whether the equations are models of the economy is a different matter, but I can, using Phillips's machine, solve those equations to within about 4%. So we'll work on going towards a simple Keynesian multiplier. The very first one is a Keynesian multiplier. We'll get to that in a minute. I'll just settle it down to an equilibrium. First thing we're going to do is balance the budget. Quite easy. So easy.
Oh, sorry. So I think this shows you what I think about analog computers. That was a feat of engineering. It was a New Zealand engineer put it forward. It was a very expensive piece of machinery. It is something that couldn't be done easily at the time. 4% error, superb. But it wasn't very long. It wasn't very long before something like this replaced it. Everyone, I mean, it was bigger, it was probably slower at the time, but eventually we don't talk about analog computers anymore. We talk about where this computer went, digital computers, and we're only going to be talking about in the long term fault-tolerant quantum computing. And that's, I'm preaching to the converted, but I think it's always best to arm the faithful with even more arguments. Okay, so what am I going to talk? I'm going to talk about noise, and I'm very specifically going to talk about Pauli channels. Why am I going to talk about Pauli channels? Well, before we do that, let's actually work out what is a Pauli channel, just so we're on the same page. A Pauli channel really is very simple. This is about the only equation I allow myself on the slides. It's really just a channel with different Pauli operators, and the Pauli operators themselves are applied with a very particular Pauli rate. And the beautiful thing about Pauli channels is that these Pauli rates, they form a probability distribution. So if we know what the Pauli channel is in a device, we have a classical description of the Pauli channel just being a probability distribution. The problem, of course, is for the type of devices we're talking about, where n being the number of elements is high, 4 to the n elements, which are all the elements of a Pauli channel, are it's a very large distribution. So even though I'm going to argue that we can kind of measure it, we can't even write it down once we get to a certain size. So part of this talk is going to be what we can do about that. Okay, so why Pauli channels? Well, the hope is, for instance, that the knowledge of the Pauli channels themselves can help us actually improve, for instance, the decoders. It can also actually help us improve the type of circuits we run. So if we know that our Paulis are biased, we can run sort of codes that might deal with that better. But also, we can tailor the decoders to actually take into account the full noise in the system, as opposed to just sort of like IID noise or incoherent noise, or even idealized circuit level noise. So, you know, this type of question, when I go and where we're talking about noise characterization opposed to error correcting, people always say, well, what about the coherent noise? And my answer to this is, well, we can always just twirl away the coherent noise. And that gets some of the engineers in the room, or the physicists who are actually improving the devices in the room, very annoyed, because they say, well, the coherent noise, if we fix the coherent noise, we can actually improve the machine. So this talk is sort of predicated on the fact that we've taken the device as far as we can, and now we're going to try and work out what we can do with the machine. And so we can twirl, we can just get rid of the coherent noise without affecting the fidelities of the machine, without making the Pauli channel worse, by doing this thing called Pauli frame randomization. It's also known as randomized compiling. And so there's a very nice experiment where that was shown to work only on a single qubit. And what you can see here is like a superoperator representation of the Pauli transfer matrix, some people might think of it as, a version of the noise. And on the left-hand side here, we see what it would be without randomization. And you can see that there are all these sort of off-diagonal elements which represent sort of rotations in the qubit, coherent noise. And then when they twirl it away, these effectively are all set to 0. And the diagonals, which are the Pauli eigenvalues, which are directly related to the Pauli channel, and I'll go through that in just a little bit of time, you know, that's all that's left. So we can engineer our systems so that they effectively have only Pauli noise in them once we've given up trying to fix the coherent noises that are in the system. Okay, so we want to measure Pauli channels, and how do we want to measure it? Well, there's sort of two main ways of doing that. We've heard a little bit about the circuit level noise, and so circuit level noise, of course, is sort of assuming that the circuits are a good description of your system. And you can do far more than just assuming like you've got 2-qubit depolarizing noise in your gates. You can actually measure what the Pauli channel is on every single one of those gates, and you can do that in a holistic way. And one of the PhD students at Sydney, Evan Hawkins, had a superb poster showing how you could do that in your error-correcting code. And that's the type of information you could directly plug into STIM, so you could simulate your circuit-level noise with real machine noise from the device that you're interested in. And then once you've simulated it, you can also take that circuit-level noise and you can put it in some sort of circuit-level tensor network decoder, like Christopher Chubb. He had another poster on that. And that should, we don't know, but hopefully that will improve your ability to decode the noise. But what I want to talk about mainly in this talk is phenomenological noise. Now, we've heard a little bit about people talking about phenomenological noise in the conference, and basically often I think what they mean there is just like IID noise. We don't really know what the noise is, so we're just going to make a single qubit error assumption. And continuing with the sort of theme of being in Australia, that's the sort of noise where I say, you call that phenomenological noise? Let me actually show you some phenomenological noise. This is from Crocodile Dundee for those who are not as old as me. Okay, so I want to measure Pauli channels. I want to measure the Pauli channels that actually exist in the device. But, that's still, what is it we should actually measure? So there's a lot of, there are a lot of papers saying, well, maybe we should measure Clifford gates, maybe we should measure generators, maybe we should measure volumes, maybe we should measure actual algorithms, maybe we should measure a whole benchmark of algorithms. Well, what about sorry, I actually don't normally have this linked up to the audio. So if I woke anyone up from a post-lunch slumber, you have my sincere apologies. But there is only one circuit I would say that matters. Well, actually, I suppose the upshot of this conference is, in fact, there are an infinite number of circuits that matter. But for your particular device, the circuit that you are going to be running is your error-correcting circuit. It's the only circuit that's going to be running on your physical qubits. What you need to do is measure the noise in that circuit that's running. All your other algorithms are going to be running on the logical layer. And I don't think the logical algorithm you're running should be affecting the noise in your physical device. So what we want to be able to measure is we want to be able to measure the noise in the computer as it's running the circuits it's going to require for quantum error correction. Okay. So we know the type of noise we want to measure. We know where we want to measure it. So the remaining question now is how can we measure? Well, there are actually quite a few remaining questions, but the next question is how are we going to measure? So there are sort of, I think, three elements that come together as to how we can measure this noise. Three tools that have sort of come from that we're pulling together. The first is, like the cornerstone of it all, is randomized benchmarking. And randomized benchmarking, it has at its heart of it a set of twirling gates. And these gates, you apply a few of them, you twirl the noise, which turns it into a sort of a depolarizing channel, which you can measure. You then do a few more gates, you measure it again, and you fit a decay curve. And this allows you to be very sensitive to even small errors, because as you lengthen the chain, you sort of the errors add up and they become easier to measure. Of course, the twirling gate in randomized benchmarking is relatively arbitrary, and the fact is that it's just twirling the noise. So when it was first started, we were looking at the noise of the gates. But if you sort of use Pauli's to twirl, you can actually twirl the noise in an arbitrary circuit. And if you twirl the noise in an arbitrary circuit, you're going to be able to measure what that noise is in the circuit. The idea is that the circuit is a lot noisier than the Pauli gates that you're using to twirl. And in fact, as they've shown in the randomized compiling paper, you can actually just compile these Pauli's in. So they don't actually add any more noise. So that's the first step. That we can twirl channels and we can measure noise in circuits of interest, which are the error-correcting circuits that we're interested in. So then how do we interpret the noise? So, when you do something like a single Pauli twirl on a device, and I should just point out, so every time in my slides I have that little ruler, probably with probability of error less than or equal to delta, so I might have missed a few. But almost every slide where I've got that little ruler, we've got actual experimental data. And I'll talk a little bit more about where this experimental data came from in a minute. But this is like a typical, I think this is called simultaneous RB, where we're just plotting randomized benchmarking results that were taken from all these qubits running simultaneously, and you sort of get a gate operation fidelity. But we're throwing away a lot of information there, and so there's a paper by Flamia and Wallman showing how we can extract a whole lot more information about this. So we can imagine that of our 4 to the n Paulis, we might be able to pick out a subset of 2 to the n commuting Paulis. And then, if you look at the single qubit measurements you make on that circuit with those Paulis, they're 2 to the n different measurements, which form a 2 to the n probability. And it turns out that there's a very simple transform, related to the Walsh-Hadamard transform, that allows you to take these observations from the one experiment. Instead of just seeing what you have on each of your individual qubits, you can actually learn the Pauli eigenvalues of 2 to the n commuting Paulis at the same time. So what is the eigenvalue of a Pauli? Well, if you think of your noise as a channel and you think of your multi-dimensional block sphere, each of the Paulis would represent an axis of that block sphere. And so the eigenvalue is showing what distortion happens to that axis. So, a pure identity channel, all the eigenvalues will be 1 and nothing happens to it. And a depolarizing channel, they all sort of shrink uniformly. But they could distort, they could become negative, bounded between 1 and -1. So we want to learn these Pauli eigenvalues, and if you've got noise that's close to the n-entity, so you're assuming that they're all positive, you can read that directly from the observations by doing this Walsh-Hadamard transform. But of course, we're only learning 2 to the n Paulis, and there are 4 to the n Paulis, so that's an awful lot of measurements you still have to do. So there's a lot of work on, being on how to learn Pauli channels. I think, you'll see from this that, for non-adaptive and adaptive, there's a scaling factor of 2 to the n, which is kind of what you'd expect if you've got to learn 4 to the n things, and you can only learn 2 to the n at the time. There's a very neat one to learn it to the infinity norm, which doesn't, it's got log n scaling. It's probably optimal. And that requires erasure channels, so let's keep the theme going. But it's also, it's only sort of approximately learning them to the infinity norm. Now, the slight problem with the infinity norm is basically you're looking for the maximum difference between your learned Pauli channel and the actual Pauli channel. And so that might be less than or equal to epsilon, except with small probability. And naively, you might think that's quite enough. The scaling was 1 over epsilon squared. So you might think, well, if I learn any Pauli to within about 10 to the -4, surely that's everything. And with the infinity norm, if the error on the Pauli is less than 10 to the -4, you can just ignore it. Just set it to 0, because that's not going to affect your infinity norm. But pulling out some experiment from the Google device, which, again, I apologize, it's sometimes difficult to know when to present the data and when to go through the experiment, but this is sort of arming you to understand what happened. There was a maximum 6-body of 10 to the -4, which is fine, and the mean 6-body Pauli error term was 10 to the -6, but there are a lot of them. And because there are so many of them, they actually accounted for almost 10% of the error budget of the device. And so if you're doing it the infinity norm, you would just ignore them, and you're missing 10% of your errors, basically. So is there a different way of doing it? Sorry, I'd forgotten about this chart. So we actually have a way of sort of winding back the error to try and pretend the device that we were measuring had higher fidelity than it actually did. But even if we wind it back quite some way, the error rates, there's still a lot of 6-body terms. They still account for almost about 1% of the error. Okay, so let's say we don't want to learn the infinity norm. Let's say we want to learn our channel. So another way of doing it is just say, well, I'm only interested in a maximum body channel. So, people talk about k-local Pauli channels. So up at the top, we've got a 2-local or a 3-local, a k equals 3 channel. And they're local because all the qubits are beside each other. Or you can talk about k-body channels where they're not local anymore, and you could just distribute them. Turns out it's just as easy to learn one than the other, basically because we're learning 2 to the n Paulis at the same time. You can learn either k-local or k-body channels at roughly an order of 3 to the k, where k is the body of the Paulis you want to learn. And that's quite good, and so there's a lot of work on that, and I'll present some results on learning k-body channels shortly. And this is obviously very closely related to all the shadow tomography work that's been going on. And it all stems from the same idea that you can learn 2 to the n things about your quantum channel at the same time. So a channel that I quite like, because it just requires one randomized benchmarking style experiment, and you can do that on people's devices before they get angry and kick you off, is something to do with locally averaged Pauli channels. So a locally averaged Pauli channel is, you obviously, when you're learning things approximately, you give up some things. So what we give up here is we give up being able to distinguish between an X, a Y, and a Z error. And so we get an average error on one qubit, we get the average error on each qubit, all the different 2-qubit errors, all the different 3-qubit errors, but we're averaging together the Paulis of that. So how does that work? Well, for instance, if you had a 2-qubit system, there are 15 Paulis in general, And then if you twirl, not using single Pauli gates, but if you twirl using single Clifford gates, you get this sort of averaging where, as I said, all the Pauli errors in one get averaged into one of the eigenvalues of this new twirl. On the other qubit, they get averaged into the other. And on the final qubit, all these 9 get averaged into the 2-qubit twirl. And of course, the beauty of this is, we're going from 4 to the n, which requires an awful lot of experiments, down to 2 to the n, which only requires a single experiment to extract all of them. And do the experiments work? Well, this is a graph that I made almost a year ago, and I've spent way too long looking at it. It's got a mesmeric quality to it, so anyone I did wake up can watch this and they'll fall asleep again quickly. And you can actually see, so the graphic on the right is where we're filling in the eigenvalues of the super operator. This was on a 2 to the 15 machine, I think, as opposed to the machine I'm actually going to be presenting. But you can see the fit, and this is running Ancilla preparation circuits. The fit is extremely good. So with data that we can take off devices today, we can really get to grips with this locally average. I'm going to call them qubit errors, this qubit error channel. Okay. So it's now time to present what this talk is actually about. Google at one point very kindly gave access to their devices to groups of researchers, and it was including Steve Flamia and myself. And outside a conference like this, if you say being able to play with the Google device almost made COVID lockdown bearable, people look at you oddly. But I think I've probably got a more sympathetic audience. Being able to play with the Google device made COVID lockdown almost bearable. And so what I wanted to do was I wanted to take, we were given various processors and they changed at various times during but towards the end we were given access to what they call the Weber device. It's a Sycamore device. A number of the qubits weren't working. I think it was originally the same device that they ran their supremacy experiment on. And of course a device like this is, by no coincidence, perfect for running something like a surface code on where you arbitrarily denote some of them as data qubits, the others still are measurement qubits. It's a rotated surface code. We've got the various ancillas, and you've got your various stabilizers in the code. It's a 5x4 code. That was the most I could fit onto the device at the time. It's fine. Everybody's familiar with the X and the Z stabilizers. And of course, part of running this code is you have a whole set of measurements you need before you can do a readout on the ancilla. It's a very sort of orchestrated plan of which gates you apply when in a very precise way to stop the circuit spreading noise throughout the device. But the thing is, you can take one of those rounds of ancilla preparation, and if you repeat it twice, you get back to the identity. So this is if you don't do the interim measurements in between. I can do interim measurements on this device, and I'll show later an experiment where you could do interim measurements and how you adapt the protocol for that. So you do a Pauli twirl in between the ancilla circuits. You do your Clifford twirl on the outside. They're all Clifford circuits. It's really easy to work out how to get back to the identity, and that allows us to measure the channel. Okay. So actually, there's another equation. So this is to talk about what correlations mean and what's independent. So two probabilities or two errors are independent if the probability of seeing an error on both qubits is the same as the probability of seeing an error on one qubit times the probability of seeing it in the other. And they're not dependent. Oh, sorry, they're dependent errors. They're not independent errors if that isn't true. And so we've got various metrics. We've got the covariance, which is basically the difference between the two. And you can sort of normalize that, and you can get a correlation matrix. So one of the things that you can instantly measure, and you can do this in a scalable way using this protocol on these ancillas, is you can actually measure the two-body correlations between the circuits. So what I've got here is a little sort of Hinton plot, and a full white square represents a value of 1. This is a correlation matrix, so it's showing the correlation between the two of them. And you can see that errors on that data qubit. So this is a simulation. There's no little thing here. This is a simulation using STIM, a fantastic tool, just using a sort of depolarizing noise, but adding in the twirls and then processing it the same way. So you can see that, the surface code works as advertised. It quarantines the errors. No matter how many rounds you do, this data qubit only ever has errors which are spread by the 2 qubit gates, which have got depolarizing noise on them. It spreads to the others. We can compress that picture, and then we can take the whole picture and do the same for every single qubit on the device. And we can see that that's all neatly correlated. And then I've just done, this is the easier way to fit it on the screen. So you'll see there's a little ruler up here. So what happens if we actually put in machine data? And we can see the two-body correlations that happened on that Google device when we actually did the protocol on it. And so there are a lot of long-distance two-body correlations, which means, of course, that the circuit model isn't being honored. There's noise in the device that's not the circuit model. And as we heard from this morning talk, it is almost certainly to do with leakage in the device. It's to do with leakage errors, not honoring the one-way sort of track of the 2 qubit gates and the very particular way of operating them, and it's allowing errors to move between the device. It could also be, control fields. It could be, in different devices, it could be frequency crowding. But the point is we've identified that there are long two-body correlations. But of course, you could do this without having the entire probability distribution. But having the entire probability distribution also allows you to count up how many, weight 2, 3, 4, 5, and 6 Pauli errors. Because you could have a correlation between 2 qubits. It's still only a two-body Pauli error. So it's also quite vital to work out what the weight of your Pauli error is here. And so, it's quite a small device. A weight 6 Pauli error being applied 10% of the time means that 10 qubits are all in error at the same time when one of those is applied. Okay. So, at the beginning of the talk, I didn't say what I was going to do, but part of our program is, trying to work out what to measure. So hopefully we've gone through what to measure and even how to measure it. The next question is it useful? Well, to do that, we had to I had to think about, well, we're trying to measure the noise in these ancilla preparation circuits. So what I should do is have an impact to see whether or not it's going to change what a predicted logical error would be. If you had a machine with that type of noise and I was actually able to do mid-circuit measurements and get the data to be able to run a surface code, does knowing this type of noise make any difference at all? So one of the ways you could do that is, when we're doing quantum error correction simulation, you sort of put up your errors. If you've got IID noise, you're just going to randomly slap a Pauli error on the different qubits. You're going to calculate what the syndrome is. You're going to see if you corrected it. I, of course, don't need to do IID Pauli noise. I've now got a probability distribution I can roll the dice on to work out what error is. Does it make any difference? And so the answer was no. So the answer was, with the noise in that device that I measured, I mean, the variance is bigger. That's presumably as a large Pauli's hit the device. It didn't make a huge difference to the logical error rate. Now I'm going to show this graph, and we're going to spend a little bit of time talking about this graph. So one is if I just assumed IID noise and I estimated what my logical error rate would be and what the actual noise would be, we're up in that top left-hand corner of the graph, and that line, of course, is where we might be expecting to have our logical error rate lower than our physical error rate. The question is, can I fill in the rest of the graph? So if you think of a Pauli channel as, well, it's a diagonal superoperator matrix, and so it's really easy to work out what multiple applications are of it in that basis. You just multiply the matrix up. So the question is, can we sort of wind back the errors in the device and say, well, what would happen? What's half that channel being applied? So if the Pauli error rate was lower but still had the same richness, can I construct what that probability distribution would look like? And the answer is you can't really, because you start getting negative probabilities at that point. Just you can't take the square root of a Pauli channel and stay in the classical regime. But it's very close, and so you can project that onto the nearest probability simplex. And this is kind of what I've done. So if you look at the correlation matrix here, for me sort of pretending the machine had less and less noise on it, but that you had still the same richness of noise, you can see the correlation matrices, so this is the two-body correlations, are pretty similar. And when you look down at the covariance matrix, so this is the one that we don't normalize, you can see the noise is getting less, even though the structure of the noise is the same. So that allows us to take this graph and sort of reconstruct, if the machine were better, would it be important to know what the actual noise was, as opposed to an IID assumption of what the average noise of the device is. And at this point, we start seeing a difference in the prediction. And this decoder isn't trying to take into account any knowledge of the noise, so I hope that would make a difference as well. But we're just here showing that knowledge of the noise is going to affect the prediction, which is what we were looking at there. Okay. So the other question we wanted to ask, so this was only a 20 data qubit device. I say only. Which meant that the probability distribution was only 2 to the 20. So it was something that could be, you could store in your computer. Once we start looking at, 60, and recently I just found myself typing 2 to the 98 into the computer and managed to catch myself before I hit return, to create a matrix of that size. We're going to have to learn how to model the data. So, this is the kind of thing when people talk about phenomenological noise, they often mean it's just independent identical noise. Just assume each of the qubits have got an independent data rate. There have been some recent papers showing that you can actually improve the decoder if you actually put in what the error rates are in each of the different qubits. Again, we can read that out, and that's a model basically where you just have one number per qubit. Perhaps an arguably more sophisticated model would be one like this, where you assume that you've got nearest neighbor correlations between the qubits. That actually allows the noise to spread, quite far through the thing. But this is a scalable model. I don't want to go into details, but we have things like sort of Markov blankets. You could see that this qubit is only going to be affected by this qubit and this qubit. And so the assumption in the model is that none of the other qubits, if you know the noise in this qubit, and you know the noise in this qubit, you have all the information you need to work out, and you know the noise in this qubit, you have all the information you need to work out. And these are the factors of the factor graph, and that's what you need to do. A qubit somewhere in the middle, you need to know you need to know 8 surrounding qubits in order to have all the information to be able to reconstruct that noise. And then, you could go to a different type of graph here where we're connecting across the width of the grid, so it's no longer scalable in the width of the grid, but it is scalable in the height. Whether it's width or height is completely arbitrary. But this type of model is obviously a more sophisticated model in that it will be better able to represent the noise. There'll be fewer model errors. And where this might be relevant is, if you've got highly biased noise and so you've got a long, skinny surface code, this would be able to sort of better represent the noise in that circuit. So the question is, are these models any good? And so we could do the same thing. We can take the noise and we can populate the models using our noise, and then we can recreate the noise from the models and see what the logical error rate would be. Basically, the models, as the noise gets lower and lower, and so it matters more and more, the different models do a better job at representing the noise than just the straight IID assumptions. The Ising model is extremely pessimistic, and part of the reason is the Ising model, that was the two-body correlated model. And I think part of the reason for that is that it sort of compresses the long-range Pauli errors into short-range Pauli errors. And on this particular small code, that probably leads to a worse result. But being able to make those models, I think, will allow us to inform the decoders, which will allow us to improve them, and it will also allow us to test what the noise is like in the systems, and maybe we can design error-correcting codes that are designed specifically to combat that noise. I'm going to go very quickly through this because I'm kind of running out of time. Looking at different types of systems, so this was before IBM officially let me play with their devices. We could take just a little 5-qubit system and we could look at just one of the stabilizer codes in this heavy hex system that IBM did. And this is one of the ones where if you take your ancilla preparation circuit once, you do your ancilla preparation circuit again, you can do midterm measurements, and you can repeat that an arbitrary amount of times. So this isn't quite the same as the error correcting code because we're doing the ancilla preparation twice and then measuring it out. But it's going to let us know what the noise is like in the system when we do that. And this is just a little 7-qubit system, and what I want to do is just pull out the Pauli channel. Now, the fact that I could do it on a 7-qubit system means I could do it in a 128-qubit system. I just had access to the 7-qubit system. So, you know, you can do all the really simple things. You can just pull out the Pauli channel in individual data qubits. And we can see here, I mean, it's well known that there's a sort of Z bias in the noise in the IBM device. Of course, we can also pull out the 2-body Paulis, and so we get a different thing. Again, we can see that there's quite a bit of ZZ noise on the data qubits that are also separated by qubits, you know. So the ZZ noise is spreading from one of those data qubits to the other data qubits. Of course, why stop at 2-body correlations when, you know, we can just run it a few more times and get the 3-body correlations. And again, you know, I think I pull out some of these to have a look at. You can see there's actually a strong ZZZ noise across 3 of those particular qubits. And across this one, less so, but there's still noticeable 3-body correlations. And then there's a little trick that, oh yeah, so I'd forgotten about this. So this is the noise. So this is the noise with no measurement. And then if we added in the measurement to see what additional noise occurred between the data qubits, there's not actually that much difference. This surprised me. This is a fantastic result. So this is a combination of using dynamical decoupling whilst the data qubits are being measured. So there's not much spreading. And then, of course, you might just want to measure all the 4-qubit noises on the 4-qubit noise in the device. I use a small trick for this, which I'm not going to go into, but it's a valid amount of the 4-qubit expression. And we can look at this little bit here, and we can see. I can't see. You can probably see better than me. There's still, you know, it's picking up all the noise from the channel. There's ZZY noise and ZZ noise, but there's not terribly many 4-qubit correlations. Okay, so that was that qubit. As I said, this is what we actually probably want to measure the noise on. It's not going to make that much difference. The circuit's a little bit bigger. If you look at the timing, I mean, people have talked about this. You can see the large measurement blocks in the timing and the little dots that are dynamical decoupling. You know, you can put this in STIM and you can look and you can see what should the correlations be if you did this code properly. And so this is a correlation matrix. It's a bit difficult to see why these correlations are there until you, you know, you might look at each of the qubits. And you can see that the code is working much as expected. The circuit level noise that you get from STIM is showing correlations over there. And then when you run it on the actual device, what do we get? Well, we're probably going to have to come back next year to do that because that is a project that we are only just starting to take the IBM devices and to start actually characterizing the noise and to try and get some logical qubits up and running and to work out, you know, whether that heavy hex code, which is a code without a threshold, or maybe you can actually fit a surface code with various methodologies, tiling that onto the IBM. So if we were to use this particular device, you know, it's a 4x4 code. So you'd probably run a 3x3 code, but you would use the circuits to work out which ones to do it. And then, of course, we've heard a lot about this. We probably want to try the Flow-K codes, or, you know, this, what was it called, the Flow-K CSS code, or whatever. And, of course, this fits absolutely naturally onto the IBM devices. It's a nice, easy tiling, and, of course, you know, there's been a lot of great work showing how we can do the boundaries of that code and how we can simulate it depending on which of the codes. And so that's all work to be done. It's all part of the work to be done during this program that we've got. We will be taking logical qubits, we'll be entangling them, we'll be using tailored decoders, and we'll be seeing how good we go. And of course, the reason I'm doing this is we had all the corporate messages on day one. This is a university message. We need 2 postdocs. So if you're interested in doing this, please come and see Stephen or myself or write to us, because we would really like to get people involved in this. And with that, I am done. Thank you.
Questions? Let's go here. Please raise your hands high so I can see it. Not yet, just a second.
It's going to be a scary question.
It's not a scary question. I was just going to ask if you read the paper that Matt and I wrote on the relaxing hardware constraints. There is a circuit in there for the heavy hex layout. So I guess it's more of a suggestion.
No, that is fantastic. So I am new to the error correcting side of things. I am very good at the characterized. Ben Brown is the other co-PI on this, and together we'll be doing that, but that is definitely a paper I will be reading.
I would love for someone to compare that to the heavy hex code and see which one's actually better. Yeah.
Well, it sounds like something we do. We'll do.
Okay, next question in the yellow with the hat.
Hello, hi. Thanks for the great talk. I guess I have a question which is more about, more of a theoretical question about the spirit of these like randomized benchmarking type protocols to understand noise. Have you considered twirling sets that are more informed by the native operations that can be done in the hardware, which might lead to twirled noise channels that aren't necessarily as exhaustive as like learning the poly noise channel, but still give you some non-trivial information about the noise in the system?
No, definitely. In a way, adding a single Clifford twirl does that, and that it averages, but it's not the only one that does it. I suppose the idea is that a twirling set, first of all, if it's the correct twirling set, gets rid of coherence, which is incredibly important. And the second thing is it determines how the different eigenvalues are in the case of the Pauli not averaged, in the case of the Clifford average. In the case of different things like the dihedral, they're averaged differently. So the question then would be how many different eigenvalues you get, and that's going to tell you how many different types of experiments you need to do to pull them out. So with the Pauli, it's, you need 2 to the n experiments of 2 to the n. With the Cliffords, you just need 1 experiment. If you did the dihedral, off the top of my head, I'm not going to put a figure, but it would be smaller. But if you had a different Kate set, yes, you could definitely have a different twirl. You just need to know how it works in how the irreducible representations.
Right, yeah, I guess my question is more about, because there's this big difference between, on the one hand, you either learn just 1 parameter or you learn 2 to the n parameters. Yep. So I'm just wondering if you do know of other twirling sets that give you a non-trivial amount of information with fewer than 2 to the n parameters, but yeah.
Yeah, I mean, it would just depend on the irreducible representations of your twirling set. Maths.
All right, thanks.
Any other questions? Okay, I see one in the back over there. And then you're next.
Hi, great talk. I'm really worried about rare errors that occur, like maybe 1 in a million or 1 in a billion, that might be very high weight. Do you think your methods could maybe detect or not detect or rule out the presence of such errors?
Yeah, that's a very good question. So single high weight Pauli errors wouldn't be picked up by the averaging method. And the reason for that is, if you're looking at the 7-body errors on a particular set of 7-body qubits, you're averaging together an awful lot of Pauli errors. So if you had, a very particular error, like a ZX, ZZ, ZY, whatever error, is going to get averaged out, and you might not see that. There is another protocol that I haven't successfully been able to run because I think it requires about 30 data qubits before it starts becoming a practical method. So again, watch this space. That will pick up single high body Pauli errors. There's a paper on that. It's called sparse Pauli estimation, and it will pick those up. Practically, I don't know. It's a watch this space, I think.
Excellent, thanks.
Next was in the front here.
Thank you for a very nice talk. So my question is about your method, powerful method that you discussed. And can we use this method to convince quantum skeptics that still thinks that scalable quantum computers are not possible?
Oh, can we convince them? You mean convince them that they are possible, even though they think?
Well, because they have some different theories how quantum computers work, and different theories of quantum noise, first of all. And can we maybe design some experiments with real hardware that can convince everyone that the way quantum noise scales is exactly as we expect it in theory?
Yeah, I'm going to have to take that question on notice. I think. I think we would have a problem with the current devices because they are too noisy, and so they would argue that the noise we're seeing just proves their point. But I think as the devices get closer and closer to being something we can error correct, we can use those protocols to show that there are no long body correlations that we don't take into account, or there are no rare Pauli spikes that we can't take into account. I mean, you can also, I didn't want to talk about it, but you can also use this, to do the sort of probabilistic error correction that various companies that I'm probably going to be working with quite like. I don't want to go down that route.
Thank you.
Okay, we have time for a couple more. Yes, over here.
Thank you for the great talk. There's been a lot of progress also in, for example, using like 2 copies or quantum memory enhanced methods to perform characterization or learning kind of physical systems. Could you comment on how those techniques may either improve or otherwise influence some of the experiments and efforts that you have here?
Probably not in 20 or 30 seconds. I mean, there are a lot of ways to measure Pauli channels, and doing it with entangled measurements, for instance, you can get all sorts of scalings with it. A lot of my work has been what type of cloud devices do I have access to, and do they support that? So I'm a, I think Steve Flamia has described me as a quantum hacker. Give me a terminal and a quantum device I can control with it, and I'll see what I can do. And so that's the answer to your question. You give me a device that supports that, a terminal, and access to it, and I'll see what I can do.
All right, well, let's all thank Robin again.